Screen 1 just shows us the basics of dilation. If we have point A and a dilation scale factor of 1.5 and a center of dilation, point P, at 0, 0, then point A prime is going to be 1.5 times as far from point P as A is. So for example, when we show the calculations, A is a distance of 5, whereas A prime is a distance of 7.5. The ratio of those two distances, 7.5 to 5, is just equal to the scale factor. Notice as well that when P is set to 0, 0, and we look at the coordinates of each point, that the ratio of A prime's x coordinate, 4.5, to A's x coordinate, 3, is equal to the ratio of its y coordinate to A's y coordinate, 6 to 4, and both of those are equal to 1.5. However, that is not going to be the case unless P is at the point 0, 0. Now, for example, we see that although the scale factor is set at 1.5, the ratio of A prime's x coordinate to A's x coordinate is no longer 1.5. In fact, they're equal to each other because P has the same x coordinate as A. When we go to screen 2, we now are looking at not just a single point, but at a pair of points connected by a line segment. So here we have AB, which right now has a length of 3.61. A prime B prime, the segment, has a length of 4.33. Well, if we look at those, we can see that the length of A prime B prime, 4.33, divided by 3.61 is exactly equal to our scale factor, 1.2. And as the scale factor changes, that relationship remains true. Notice that when the scale factor is set to 1, the two are exactly coincident, which means they occupy the same place. Notice here that we've also done a calculation of the slopes of AB and A prime B prime, both of which are equal to negative 0.67. The fact that they have the same slope means that these two line segments are parallel, as we can see here. Also notice that when we connect these with rays to point P, that the ray passes through A and A prime, and it passes through B and B prime, and that as we move B, B prime stays on the same ray, and as we change the scale factor, A prime and B prime just move along those two rays, either closer to point P or farther away from point P, depending on whether the scale factor is less than 1 or greater than 1. When we get to screen 3, we now have two figures. We have triangle ECD and we have triangle E prime, C prime, D prime. So all we've done is we've dilated each of these 3 points. We've created a new triangle. Notice when we look at the ratio of the areas of these two triangles now, we see that the area of E prime, C prime, D prime is equal to 12, whereas the area of ECD is equal to 3. The ratio is not equal to our scale factor of 2, it's actually equal to the scale factor squared, or 4. If we set the scale factor to 3, although we can't see it, the ratio of the two triangle areas is 27 to 3, or 9, which is equal to 3 squared. If we set the scale factor to 4, the ratio of the two areas will be 48 to 3, or 16, which is equal to 4 squared. Again, when we show the rays, all we're doing as we change the scale factor is removing points E prime, C prime, and D prime along the rays that connect point P to our original triangle vertices E, C, and D. When we move to screen 4, now what we're trying to do is LMN and L prime, M prime, N prime. One is a dilation of the other. So LMN is the original. We're trying to find this scale and the center of the dilation. You'll notice that in this case, P does not actually affect the dilation. P is not the center of dilation. So the question is, how do you find the center of dilation? Well, remember that if we draw a ray from the center of dilation through L and L prime, they will fall on the same ray. Similarly, M and M prime will fall on the same ray, and an N prime will also fall on the same ray. So if you draw a ray through N, N prime, M, M prime, and L, L prime, where those three rays intersect, which should be down here somewhere, that will give you your center of dilation. Your scale of dilation will come from figuring out what is the ratio of the distance of the center of dilation to L prime divided by the distance of the center of dilation to L. That will give you your scale of dilation. It looks as though L prime will be closer to the center of dilation, which means that your scale factor will be less than 1. You can see that as well by the fact that the triangle is L prime, M prime, N prime is smaller than the original triangle, LMN. The same thing is true here when we go to screen 5, except that now we are dealing with not a triangle, but a quadrilateral. So one of the things that if you want to find the center of dilation is if you move Q so that Q and Q prime are occupying the same space, that has to be the center of dilation. So that's an easy way to find the center of dilation. The scale of dilation, again, you'll have to find by measuring the ratio of the distance of the center of dilation to O and the center of the dilation to O prime, and divide their distance, center of dilation to O prime, divide that by center of dilation to O. Again, it looks as though O prime, S prime, R prime, Q prime is larger than OS, RQ, so the dilation will have a scale factor greater than 1.